We want to talk about a gravitational wave detector, and specifically what we want to look at is the fact that the precision on the wave detector is extremely high, and it's actually better, significantly better than the diameter of a proton. So that's what we want to get to. We want to come up with an estimate of what that precision actually is. And we have confidence in that precision because that precision was actually measured in a gravitational wave. The announcement for the detection of the gravitational wave was through a Caltech news release on the 11th of February 2016. Today happens to be the 24th of March the same year. Then on the 12th of February, the science paper appeared in Physical Review Letters by Abbott et al. And about 1,004 co-authors. The title of the paper was Observation of Gravitational Waves from a Binary Black Hole. The system whose sensitivity we're interested in is called LIGO, L-I-G-O, and that stands for Laser Interferometer Gravitational Wave Observatory. And there are two observatories. One's in the state of Washington and the other is in the state of Louisiana. And they consist of two laser interferometer arms, each 4.0 kilometers long. And what was observed, it was actually observed in 2015, the gravitational wave. And in terms of the strain they measured, it looks something like this. This is a time axis here, and what I'm indicating here is that the frequency of the gravitational wave was about 35 hertz here, and it went up to 250 hertz by the time it disappeared. Clearly this is not the scale. And through a fit to Einstein's field equations, using the signal, they were able to come up with a distance to the merger of the two black holes, binary black hole merger, so there's two black holes, they merged. So they could find the distance and the masses that were involved. If you look at this change in frequency as a function of time, it's a chirp, low frequency to high frequency, kind of sound that a bird might make. And Professor Charles Meisner suggested an interesting name for that chirp, and he called it the Hallelujah chirp. People have been waiting for a long time to see this, so it seems like a very appropriate name. Now, if you go to the paper, here's some words taken out of that paper. The peak gravitational wave strain was 1 times 10 to the minus 21. Now, strain refers to a change in length over the original length. So if I could stretch this marker a little bit, that change in length would be the delta L, and the original length would be L. And that strain that they were actually able to measure, indicating what the precision of the LIGO system is this 10 to the minus 21. So the length, as I indicated back over there, is actually 4 kilometers. So if we want to find out how small this change in length was of the laser interferometer arm, we would just solve for the delta L, and that would be equal to the length of 4 kilometers times that number, which will be just 4 times 10 to the minus 21. Kilometers. So we need to change, we want to get down to a unit that's familiar when you talk about the size of a proton. So we want to convert this to something more convenient. So there's 1,000 meters in 1 kilometer. And you can see this is a very small number. And there is a unit called an atto, A-T-T-O meter, or AM, abbreviated AM. And that is equal to 10 to the minus 18th meters. So we'll put that in here. And if you work that out, there's 10 to the 3 here. It brings us to 10 to the minus 18th. So this is equal to 4 times 10 times 10 to the minus 18th if we kept this part of the units, but we're going to convert to attometers. So it works out to 4 AM, an extraordinary small number. Now the charge radius on a proton is generally taken to be something like 0.88 femtometers. And a femtometer is 10 to the minus 15 meters. So that's the charge radius of the proton. So what we can do is we can take the 4 attometers that we have here and we can say in terms of the diameter of the proton, which would be 2 times 0.88 femtometers. So we have 10 to the minus 18th here, we have 10 to the minus 15th here, and if you work that out, you get 0.0023 diameter of the proton. Let me write that out here. So that is approximately the precision that was used to detect the gravitational wave. So it's a small part of the diameter of proton, and roughly speaking, that's 1/400th of the diameter of the proton. Extremely small number. And if you notice what was put out for the public, that was listed as approximately 1,000th the diameter of a proton. So all we did was use the actual strain signal for the gravitational wave that was detected, and we converted that to units of the diameter of a proton, and we found it to be 1/400th the diameter of a proton, or roughly 1/1000th the diameter proton. So those 4-kilometer long arms, when the gravitational wave interacted with them, changed their length by roughly 1,000th the diameter of a proton. A very, very small number. Very high precision.